In this video, we're going to talk about operational transforms, or as it's called in your textbook, Laplace transform properties. And so what we want to do is we want to know the effect in the frequency domain of performing an operation in the time domain, or vice versa. So we want to know the effect of doing some operation in the time domain on the function in the frequency domain. And so one example of this is we said, let's say we have u of t. Well, we know that the Laplace transform pair for our u of t is 1 over s, but maybe we make some changes to our u of t in time. So maybe we multiply it by 6, and maybe we shift it in time by 5. So we want to know, how does this affect our frequency domain? And so our operational transforms are going to give us a way to easily do that. And so let me say that for all of these properties here, or most of them, I'm going to be just presenting the end result. But if you want to go back and see how you can find or derive this property from our equation 1, our Laplace transform definition, you can see pages 678 to 684 in the textbook. Okay, so let's just sort of go through a lot of these. So our linearity, which is just going to be multiplication by a constant. So let's start simple here. Let's see if I can spell multiplication. There we go, I think. So multiplication by a constant. So this is our linearity property, and we're looking at multiplying by a constant. So let's assume that our Laplace transform of some function f of t is equal to capital F of s. So what we're saying then is if we want to know the Laplace transform of some constant k times f of t, what does that equal? And so again, if you want, you can see how that's done. In this case, it's pretty simple because our k comes out of that integral, so we just get k times f of s. So multiplying by a constant in frequency corresponds to multiplying by a constant in time, and vice versa. Okay, so now let's also look at another one related to linearity, and that's going to be addition and or subtraction. So addition and or subtraction. Okay, and so in this case, we're going to consider a few different ones. So we're going to say, let's say our Laplace transform of some function f1 of t is equal to f1 of s. And then let me just copy that and paste for our next couple, because they're going to be the same. Okay, so let's say we also have, put one over here. So let's say that we also have the Laplace transform of f2 of t is equal to f2 of s, and the Laplace transform of f3 of t is equal to f3 of s. So this is sort of our starting point. We know these three functions and their Laplace transforms. So now, what if we wanted to find the Laplace transform of f1 of t plus f2 of t minus f3 of t? And again, this one is pretty straightforward in terms of our integration, because we can break the integrals up and have three integrals. So our end result is we have the Laplace transform of that is f1 of s plus f2 of s minus f3 of s. So that would be our addition or subtraction property. So let's look at a few more in this video, and then we'll come back and finish them up in a later video. So the next one we want to look at is scaling. So again, let's just keep in mind, let's say we have this general Laplace transform of f of t is f of s, unless we say otherwise. So let's say we then want to know the Laplace transform of f of a times t. So we're scaling this in time. And so it turns out that this is 1 over a times f of s divided by a. And so in this case, a is a constant that's greater than 0. Okay, so that would be our scaling property. So what about another common thing, which we saw in the example I wrote at the start, is a time shift. So I talked about shifting that step function by 5. So let's say we want to know the Laplace transform of f of t minus a. And so to be explicit, I'm going to say we have u of t minus a. And so the u of t minus a is just saying that it's still defined at that same point where it was 0, but now we've just moved it to either, well, so we're going to move it to the right. And so what this gives us is e to the minus as times f of s. And so in this case, we have a is again going to be a constant. In this case, it's greater than or equal to 0. Okay, so that's how we deal with time shifts, or shifts in the time domain. Well, what if the sort of operation is reversed? So what if we have a frequency shift? And so it turns out that this is going to correspond to Laplace transform of e to the minus at, f of t, u of t. Again, the u of t is just there to explicitly define these functions for t greater than 0. And this corresponds to a shift in our frequency domain, f of s plus a. So if we're shifting in frequency domain, we just have this e to the minus at that comes up in our time domain. So in the next video, we're going to take a look at a handful of other operational properties, but ultimately what we're going to see is similar to our table of common pairs, we're also going to have a table of common properties that we use.